In this video, I'm going to talk to you about how we calculate uncertainties in our results. So you can see here, I've got some results for a pendulum, this is. So a pendulum would be something like this. Here's a mount, here's the string, and there is the pendulum bob. And you can see that what we're going to do here with this pendulum is displace it. So this is a piece of string. This is your mount. This is just a weight on the end of the string. We call it a pendulum bob. And we're going to displace that up to here. Okay, and then we're going to release it, and it's going to swing backwards and forwards like this, isn't it? It's a pretty poor diagram, but swing back and forwards. So we release it from here, and it's going to swing this way and then back again. That is one whole oscillation, and the time taken for that is called the time period. And what we're going to do here is we're going to vary the length of this string. I should measure it maybe to the middle of the bob there. That's 1 meter. We can vary that length anywhere between 0.2 meters and 1 meters. Anywhere between 0.2 meters and 1 meters, we're going to vary that. In fact, you could vary it from 0 meters, I suppose, really. But we're going to vary it from 0.2 to 1 meters, and we're going to measure the time period for each of those lengths. And you can see here that we've measured 5 different lengths of the pendulum and measured the time period 3 times for each of those lengths. Okay. So, taking those results now, I want to calculate the uncertainty. Now, before I do that, I should say that all of these results are recorded to the resolution of the stopwatch. Now, we know the resolution of the stopwatch is 0.01 seconds. How do I know that? Well, because all these results are recorded to 2 decimal places. So that tells me that my resolution here, is plus or minus 0.01 seconds. And I know that because in physics we always record our results to the resolution. Okay, here I know that the resolution is 0.001 meters, or plus or minus 0.001 meters, because again in physics we always record our results to the resolution of the instrument that we use to measure it. Okay, so we know that that's the resolution. Now, having said that then, let's try and calculate the uncertainty in our results. So we want to calculate the uncertainty in our result for, let me just move this paper up here a minute. We're going to calculate the uncertainty in our result for the 0.2 meter length. Okay, so 0.2 meters. Now, the first thing you do to calculate the uncertainty is you work out the range of your results. So you can see here that 0.89 is our largest time period, 0.83 is our smallest time period. So to calculate the uncertainty, and we call this the estimated or absolute uncertainty. Estimated or absolute uncertainty. You can use either of those terms. That's going to be 0.89 minus 0.83 divided by 2, which is going to give us 0.06 over 2, which is 0.03 seconds plus or minus. So that is the estimated or absolute uncertainty in my measurements of time period, half the range. Okay. Now, let's do the same thing for 0.4 meters. We'll just call it the estimated uncertainty this time. Same thing as absolute, but we'll just call it estimated. So 1.28 minus 1.27 over 2, half the range. Largest reading, take away smallest reading. Okay, and that's going to give me 0.01 over 2, which is 0.005 seconds. Now, this is less than the resolution of our stopwatch. So in this case, you don't use this. We say that the estimated uncertainty is equal to plus or minus 0.01 seconds. If you calculate half the range and it's less than the resolution, you use the resolution as your uncertainty. Okay, now what about this? If you've got the 1 meter length here, the estimated uncertainty here, you might say, well, look, we've taken 3 readings, they're all the same, so there's no uncertainty because there's no range. Well, that's just not true. There cannot be 0 uncertainty in any reading. So what you do here is, because there is no range, again, you use the resolution. Okay. Now, what about if you haven't taken multiple readings? Now, if you look at the length here, if we want to work out the uncertainty in our length, by the way, these are all estimated uncertainties in the time period. Okay, so all right, they were all estimated uncertainties in the time period values. If I want to work out the uncertainty in my length values, so estimated the estimated uncertainty here, because we've only calculated the length once, we've only measured the length once, I should say, we can't calculate a range. So what you do is you just use the resolution, which we know is that plus or minus 0.001 meters. I know that because this is recorded to 3 decimal places. So the smallest variation we could have is 0.001. That's the resolution. Okay, so to recap, if you've got multiple readings taken, to calculate the estimated uncertainty, you calculate half the range. If half the range is less than the resolution, you use the resolution as your estimated uncertainty. If there's no range, you use the resolution. And if you've only taken 1 reading, you use the resolution as your estimated or absolute uncertainty. Okay. Now, this brings us on to percentage uncertainties. So what about percentage uncertainties? We need to be able to calculate these. Now, a percentage uncertainty is equal to the estimated uncertainty, or absolute uncertainty, whatever you want to call it, divided by the mean value multiplied by 100. Okay, so if we do that for percentage uncertainty in the time period for 0.2 meters, we can do this. We know from earlier on that the estimated uncertainty was 0.03 seconds. We calculated that earlier here. Okay, 0.03 seconds. We know that the mean value in that time is 0.87 seconds. So we divide those and then multiply by 100. Whoops. And that's going to give us our result here. Okay, and if you type that into a calculator, you'll get 3.45%. Okay, and we're going to quote that to 1 significant figure. That's something I should have perhaps mentioned earlier. Whenever you calculate an uncertainty, when you're quoting a final answer, you quote it to 1 significant figure. Within a calculation, it's fine to use more than 1 significant figure, but when you're quoting a final answer, it's 1 significant figure. Now, if we do the same thing for some of the other values that we've used, let's think about perhaps the 0.4 meter one here. So the percentage uncertainty in T for 0.4 meters. Again, the way you do this is you just take your estimated uncertainty. Now, if you remember earlier, our estimated uncertainty here was 0.01 seconds, the resolution. So you take that, divide it by the mean value, and the mean value here is 1.28, and you multiply that by 100, and that's going to give you 0.78%. If this is our final answer, we record it as 0.8%. Okay, and you can put a plus or minus in front of those actually as well. One more then. If you do the one for the 1 meter value, okay, percentage answer in T. Well, we know from earlier that the estimated uncertainty in my 1 meter value was the resolution, because there's no range, so the uncertainty in that time period was the resolution. I divide that by the mean value, which is 1.98, and I times by 100, which is going to give me 0.5% to one significant figure. Okay, so that's how we calculate percentage uncertainties and estimated and absolute uncertainties. All right, so the next video I'll explain how to combine uncertainties. Let's leave it there for now.